All right, so finishing 16.8. So as you can see, we finished this. No, actually we didn't. We kind of miraculously came up with pi. So we're going to actually go back and finish this one the right way, and then we'll do the other problem. Should hopefully be about a 10-minute video. We'll see. All right, so I had to erase the next line because with the incorporation of the extra r in the 2r sine theta, we have to distribute the r throughout. And because of that, we cannot separate this one, unfortunately. So we are going to have to take the antiderivatives as they stand right here. So let's see, the way I have it set up, we're going to have to do this with respect to theta first. So this is going to be r theta. This is going to be, let's see, that's going to be plus 2r sine squared cosine theta. Yeah, that looks right. We'll evaluate that from 0 to 2 pi. And then don't forget 0 to 1 dr. All right, so plugging in 2 pi, we are going to get 2 pi r plus plugging in 2 pi for cosine is going to give us 1, so that's going to be 2r squared minus plugging in 0 for theta, we get 0 plus plugging in 0 for the cosine part of theta is going to give us 2r squared. Well, that actually kind of works out nicely because it looks like the 2r squareds are going to go away. So I am left taking the antiderivative here of 2 pi r from 0 to 1. So that's going to be, what's it going to be, r squared. So it's going to be pi r squared from 0 to 1. And fortunately, this does work out. Plugging in 1, plugging in 0, we get pi. So we kind of miraculously got there last time because we ran out of time during class, but there you go. It actually does work out to pi. All right, one more. All right, example 7, consider the surface S described by the paraboloid z equals 16 minus x squared minus y squared, as you see in the drawing on the left. And there's a typo that should say for z is greater than or equal to 0, not 2, as shown in the figure. All right, we're going to verify Stokes' theorem for the surface S described above the vector is described above and the vector field that's given as 3y 4z minus 6x. So on this first one, we're going to do the line integral. F dot dr. So again, what we're going to need to do is we're going to need to parameterize this thing. So we're going to have x equals, well, let's see, our curve, which is what we're talking about here. I'm sorry, yeah, our curve is really this piece right here. And it does need to go counterclockwise. And if we look at this thing from above, coming straight down, we can just use our standard polar or cylindrical coordinates. So x would be cosine theta. Now remember, this is parameterizing the curve, so it's just the outside piece. So, whoops, go back to black on that one. 4 cosine theta. Y is going to be 4 sine theta. And z in this case is 0. So that's really going to give us our f of r of t, or in this case r of theta. R prime is going to be the derivative of each one of those pieces. So the derivative of the x part is going to be negative 4 sine theta. Y part is 4 cosine theta. And the z part is 0. So now f of r of t is going to be, so I'm going to have to plug x, or excuse me, I'm going to have to plug y into the y right there. So that's going to be 3 times 4 sine theta. So we're going to get 12 sine theta. For the middle part, middle component, it's 4 times z. Well, that's 0. And then the last part is negative 6 times x. So that'll be negative 24 cosine theta. And then we're going to need to dot those things. So we're going to take an integral from 0 to 2 pi, because it's a circular base. Dotting these things, we're going to get negative 48 sine squared theta. The middle one is 0. The last one is 0. That's wonderful. D theta. So we'll use our sine squared reduction formula. 0 to 2 pi. The 1/2 I can just multiply times the negative 48, and we'll get negative 24. That the 1/2 is taken care of, so 1 minus cosine 2 theta d theta. All right, now we're ready to go ahead and take the antiderivative. So negative 24 theta minus 1/2 sine of 2 theta from 0 to 2 pi. So again, plugging 0 in for theta will give me 0 throughout. Plugging the 2 pi in for theta, the sine part will give me 0. So really, plugging 2 pi into here is the only thing that gives us a value other than 0. So we're going to get negative 24 times 2 pi, or negative 48 pi. All right, so now we're going to have to verify that that is going to give us the same thing as the curl of f dot ds and the double integral of that over s. So we'll go to the second page to do that. So first thing is, let's find the curl. I, j, k, d dx, d dy, d dz. And looking back at the first page was 3y, 4z, and negative 6x. Yeah, that's it. Okay. All right, so let's go ahead and find our curl here. So eliminating the I row and column, I'm going to take the derivative of negative 6x with respect to y, which is 0, minus the derivative of 4z with respect to z, so that's minus 4. Eliminating the j row and column, the derivative of negative 6x with respect to x is negative 6. The derivative of 3y with respect to z is 0, so negative 6, but we change the sign, so that becomes positive 6. And then eliminating the z row and column, or the k row and column, it's going to be the derivative of 4z with respect to x, that's 0, minus the derivative of 3y with respect to y, so that's minus 3. So there's our curl. Now we need to establish our surface, S. All right, so I think we have to go back on this one. Okay, so the surface, we can actually parameterize right now in terms of x and y, and we can change it to polar later, or you could parameterize it in terms of polar right now and then not have to worry about changing it to polar later. Because of the numbers and the x's and the y's that are there, I think this is easy enough just to go ahead and parameterize in terms of x and y first, but you can choose to do it the other way if you want. I'm going to go with the trivial. X is x, y is y, and then shoot, I already forgot what z is. Z is 16 minus x squared minus y squared. Z is 16 minus x squared minus y squared. And the reason I leave it like this is just because doing the r sub x, r sub y, and then the cross is actually really easy to do with these specific values in this case. So partial with respect to x is going to be 1, 0, negative 2x. Partial with respect to y is 0, 1, negative 2y. And then we need to cross those to get our normal vector. And let's see, crossing that, let's see, that's going to be negative 2y, right? Yeah, negative 2y. No, that's not right. Eliminate the I row, I column, I'm sorry. That's 0 minus 2, 0 times negative 2y, that's 0, minus a minus 2x, so that actually gives me 2x. J row and column is going to be negative 2y minus 0, but we changed the sign, so it's positive 2y. And then eliminating the J row and column just gives us 1, so we do have a positive orientation there, which is good. So then we need to take the dot product of the curl and a parameterized surface. So we're going to have the integral over d. Dot product, this thing is going to be negative 8x plus 12y minus 3. So you could leave this in terms of x and y. You just have to do a circle, and your bounds are going to have positive and negative square roots and stuff like that in it, or we could change it to polar, which again is probably, I don't know which way you find easier, but for me polar is going to be the easier method. So we're going to go ahead and change this into polar. So we know that x is r cosine theta. Now, this is where I need to kind of go back, because I know we were struggling, or I was personally struggling with this. So this piece right down here is, whoops, let me start that over again. This piece right here, this is the piece right here that goes around the outside. Kind of looks like something like that. Goes around the outside of the base of this thing, which is really the blue part on the side. If we go back to the general idea that we had here, let me see if I can find it. I know the video is running longer than I said, but I know you guys will 2 times speed it anyway, so it doesn't matter. So if we go back to this, I was thinking about this. So the idea of this thing going through the net, all this water that's coming down is actually going to go through the entire surface here. So it's not just going through the ring, it's going through the entire surface of what that ring encompasses. So it's got to go through the entire surface, which is why the radius can vary on this thing. It's not just the outside cylinder here. It's going to be the outside cylinder and all the pieces on the inside of this net. So that's what we're looking at. That's why we have to do this in terms of r cosine theta and r sine theta, because it's got to go through this entire thing right here. It's the entire space. So that's why the r can vary. I hope that makes a little bit more sense. It's starting to me, so I'm hoping that it will to you guys as well. So back to the actual antiderivative. So it'll be negative 8 r cosine theta plus 12 r sine theta minus 3. And then we are changing this into polar, so we're not parameterizing it in polar, we're changing it into polar. So this is going to be r dr d theta. And let me erase that d, it's a little big. So our double integral, so I've got r on the inside. So r in this case is going to vary from 0 to 4, because I believe 16 was the other side of the, was the outside of the circular base. And then of course 0 to 2 pi. And, okay, well, the good thing is that there's no squareds or anything like that. Can't split it, though, because I can't take an r out of everything because of that 3 on the outside. So we just have to do the straight integral. So antiderivative with respect to r, negative 4r squared cosine theta plus 6r squared sine theta minus 3r from 0 to 4. All right, plugging in a 4 squared times 4 is going to be negative 64 cosine theta. 4 squared, 16 times 6 is 96, I think. Yeah, 96 sine theta minus 12. That looks right. We'll find out in the end, because if it doesn't give us the right answer, we'll know. All right, antiderivatives. Now with respect to, I lost something, didn't I? Because this is getting way too easy. This should not be this easy. What'd I lose? Oh, I took the antiderivative from the wrong spot, I think. All right, yeah, that was way too easy. Yeah, antiderivative here should be negative 4/3 r cubed cosine theta. You guys are probably watching this video thinking, Mr. McCoy, what are you doing? It's a good question. I don't know. So that's going to be 3r cubed sine theta. Wait, no, I'm still doing it wrong. Holy cow. Let's just wipe this whole second and third line off of here. All right, what I forgot to do was distribute the r. That's where the problem comes in. Hopefully you guys are way ahead of me by now, and maybe you've already got the answer and you're done watching. So if not, stick with me. I will get this right eventually. All right, now let's try it again. Antiderivatives with respect to r, negative 8/3 r cubed cosine theta plus, what's that, it's going to be 4r cubed sine theta minus 3/2 r squared from 0 to 4. So plugging in 4, 64 times 8. Well, 64, I don't know. I'm just going to write it as 64 times 8. I just don't feel like figuring it out right now. That's going to be 64 times 4, so I think it's 296, but I'm just going to write it as 64 times 4 sine theta. This one I can figure out. That's going to be 16 over 2, 8, so negative 24. Oops. All right, antiderivatives now. So that's going to be antiderivative of negative cosine is negative sine, so negative 8 times 64 over 3 sine theta. This is actually going to work out. I don't need to worry about the numbers, which is good. Antiderivative of positive sine is going to give us negative cosine minus 24 theta. That's the only part that's actually going to matter. And the reason for that is because I am going from 0 to 2 pi. Plugging in 0 and 2 pi into both of these are going to give you 0, because you're going to get the same thing minus itself. But the only thing that's going to matter is plugging in the 2 pi into the negative 24. So we get negative 24 times 2 pi, or negative 48 pi. So it does work after a lot of silly mistakes. All right, kept it to about 20 minutes, so you guys will finish it in about 10.